Today I will continue my convection topic in part 2, as we have already got the concepts of convection. Now we will discuss forced convection. First of all, we will consider forced convection in laminar flow, and the flow is steady. Then in the boundary layer zone, we can apply fundamental laws of physics: conservation of mass, conservation of momentum, and conservation of energy. All the equations have been given in the slide, where u and v are the velocity in x and y direction respectively. Similarly, alpha is the thermal diffusivity. As we all know that for a flat plate, the free stream velocity of the fluid is constant. Therefore, its first derivative with respect to x, that is the direction of flow, will be 0. Now in forced convection over a flat plate, as we discussed in the last slide, we want to evaluate the values of coefficient of friction and convective heat transfer coefficient by solving the equations of conservation of mass, momentum, and energy equations. These equations can be solved approximately numerically, that is, its exact solution can be obtained. By solving these equations, we can get the empirical formula. This empirical formula can be expressed as Nusselt number, that is HL upon K, is a function of Reynolds number and Prandtl number, where C, M, and R coefficient depending upon the geometry of the boundary. Now, in this slide, I am showing the exact solution of that equation given by the Plossius. As per that solution, boundary layer thickness will be delta upon x is equal to 4.99 upon root of Reynolds number, local Reynolds number, where x is the distance of the place we want to evaluate the boundary layer thickness, and delta is the boundary layer thickness. Similarly, skin friction coefficient can be obtained by this formula, which is defined as the ratio of wall shear stress and half rho u infinity square. It may be given as 0.664 divided by root of local Reynolds number. Okay. Likewise, we can get the values of average drag coefficient, which is defined as the average of this skin friction coefficient over the length of the plate. Similarly, local Nusselt number based on the position at which we want to get the value. And similarly, if we do the average of these values, then it is average Nusselt number. These all the values are for forced convection over a flat plate laminar flow. Similarly, in this case, we can evaluate the values of local heat transfer coefficient using this formula and average heat transfer coefficient by the formula. All these formulas are not needed to be crammed. What we can do, we can use them directly from the heat transfer data book. Okay, the properties which are required for calculating all these values, like say thermal conductivity. For Prandtl number, you require dynamic viscosity, specific heat of the fluid. These all the properties can be obtained from the heat transfer data book. This is very, very important. And the values of the properties will be evaluated at film temperature. Film temperature is the average of surface temperature and the temperature of the free stream fluid. Okay, this is very important that all the properties will be evaluated on film temperature, and we can evaluate or get the values of the properties using the heat transfer data book. There is no need to cram these formulas. Now, based on the previous solutions, we can have curves. As we can see, that the hydrodynamic boundary layer keeps on increasing as we are moving in the downstream direction. Similarly, we can see thermal boundary layer. It is also increasing, but if you can see the convection coefficient H, then we can see it keeps on decreasing in the downstream direction. Initially, this decrement is very fast. Okay. Similarly, similar analysis can be done for turbulent boundary layer. As shown in the figure, laminar region is in the upstream direction, and thereafter in the downstream direction we got the turbulent boundary region. Now we will discuss the forced convection over a flood plate when turbulent flow is there. In that case, Reynolds number can be obtained using this formula. Okay, and then by using these formula, coefficient of friction, coefficient of drag, local Nusselt number, average Nusselt number, we have to use these formula. All the formulas are given in heat transfer data book. Okay, after getting the value of Nusselt number, we can easily get the value of convective heat transfer coefficient, which is the ultimate objective, so that we can find the heat transfer rate using the formula of Newton's cooling law, H8 Ts minus T infinity. Now see the laminar boundary layer development. It's clear. It can clearly be seen that the boundary layer grows as we move in the downward direction, and the profile is delta is proportional to root x. Means initial growth is fast, and thereafter that growth rate becomes smaller. That growth rate is 1 by root x. Similarly, if we see the wall shear stress in case of laminar boundary layer, it can clearly be seen that as we move in the downstream direction, the wall shear stress keeps on decreasing. This decrement is very fast in the initial length of the plate, and thereafter it becomes almost constant and becomes less stiff. We can also consider the forced convection when there is a combination of laminar and turbulent flow. It can happen when the plate is sufficiently long so that the flow becomes turbulent, and we should use the average values of coefficient of friction and Nusselt number. That we can see that for calculating the coefficient of friction, what we have done, we will average the values. As shown in the last slides, if we perform the integrals and simplify them, we will obtain these expressions for the Nusselt number and the coefficient of friction. By using these formula, we can easily calculate convective transfer coefficient and coefficient of friction. These all the formulas are given in the design data book. Now, these above relationships have been obtained for the case of isothermal surfaces, but could also be used approximately for the case of non-isothermal surfaces. In such cases, assume the surface temperature be constant and some average value. For isoflux case, the local Nusselt number for laminar and turbulent flow can be found from these expressions. This is very important to note that isoflux relationship gives values that are 36% higher for laminar and 4% for turbulent flow relative to isothermal plate cases. So this is all about forced convection. Now we will try to understand free or natural convection. So first of all, we should know what is free or natural convection. Natural convection is a mechanism or type of heat transport in which fluid motion is generated only by density differences in the fluid occurring due to temperature gradients. This is very important. The density difference is there just because of temperature gradient. As we know that the plate on which the flow is made, the temperature of the plate is somewhat different than the temperature of the fluid. Because of that, density difference is there and flow is taking place. There is no external source like a pump, fan or suction device is there. These are some real life example of natural convection. Boiling water, in that case the heat passes from the burner into the pot, heating the water at the bottom. Then radiator puts warm air out at the top and draw in cool air at the bottom. Similarly, steaming cup of hot tea, the steam is showing heat being transferred into the air, and ice melting, heat moves to the ice from the air. Now, one more example by which we can easily understand the natural convection is the hot egg which is exposed to the cooler air. In the figure, it's very clear that the cold air tried to replenish the warm air, and because of that, flow is there in the upward direction, because warm air has the less density than the cold air, and because of that, flow takes place. The heat transfer that is enhanced as a result of this natural convection current is called natural convection heat transfer. Now, free convection. Again, we will try to understand a free convection flow field is a self-sustained flow driven by the presence of a temperature gradient. As opposed to a forced convection, where external means are used to provide the flow. Okay, so this is very important to learn that in case of free convection, density difference is responsible for the flow, and this density difference we get by temperature difference. Now, basic definitions. Now we are considering a hot plate. You can see this hot plate is vertical, okay, and surrounding fluid is cold. The plate is warm because of this upward force acts, that is equal to rho infinity minus rho into g into volume. Okay, this is called buoyancy force, and this effect is called buoyancy effect. In this case, this density difference is very important. Okay, the density difference is due to the temperature difference, and it can be characterized by the volumetric thermal expansion coefficient beta, which is defined as the rate of density change with temperature multiplied by 1 by rho. You will take negative of it. So delta rho will be almost equal to product of the volumetric thermal expansion coefficient and the temperature difference. Now we will define a very important non-dimensional parameter, just called as Grashof number. Grashof number, it is the ratio between the buoyancy force and the viscous force. As we already discussed that in case of natural convection, the dominant force is the buoyant force. It is not the viscous force. So Grashof number is defined as the ratio of the buoyancy force and viscous force. So we get this formula. In formula we can easily see that X ratio to gravity is playing important role. Volumetric thermal expansion coefficient beta is very important, and in the denominator viscosity is there. Now it is very important to note that Grashof number replaces the Reynolds number in the convection correlation equation. As in case of forced convection, Nusselt number was a function of the Reynolds number and Prandtl number. But in this case, in case of natural convection, Grashof number is a function of Nusselt number is a function of Grashof number and Prandtl number. In free convection, bioinertia driven flow dominates the flow inertia. Therefore, the Nusselt number is a function of the Grashof number and the Prandtl number alone. Now, there is a concept of Rayleigh number also. In many instances, it is better to combine the Grashof number and the Prandtl number to define a new parameter called Rayleigh number. Rayleigh number is a product of Grashof number and Prandtl number. Its main use to characterize the laminar to turbulence transition of a free convection boundary layer flow. That by giving a limiting value, we can identify whether the flow is laminar or turbulent. For example, when Rayleigh number is more than 10 raised to the power 9, the vertical free convection boundary layer flow over a flood plate becomes turbulent. This is for the flood plate, hot flood plate, hot vertical plate. In this case, if the Rayleigh number is greater than 10 raised to power, then the flow will be turbulent, otherwise laminar. Now we will consider the steady laminar free convection over vertical plate. We can easily see that we are considering the flow in the upward direction. X is aligned along the upward direction. Now we are considering this hot plate. We are assuming that this flow is steady, laminar, and two-dimensional. And similarly, the fluid to be Newtonian with constant properties. That properties are not changing with temperature, including density. Okay, the velocity and temperature profile for this vertical hot plate is shown in the figure. Now, for solving the problems related to free convection, we will use heat transfer data book as in the case of forced convection. In the following slides, some formula has been given for the free convection for different geometrical cases. Okay, in this case also all the properties will be calculated at film temperature. That is the average value of surface temperature and fluid temperature. Okay, then coefficient of thermal expansion, we know it is the reciprocal of the fluid temperature. Nusselt number we know HL upon K. Grashof number, it is given in data book at page number 134. By putting all the values in these units, we can easily get the value of Grashof number. It is very important to know the units. We have to put unit given in the slides. Okay, if GRPR, that is Rayleigh number, is less than 10 raised to power 9, flow is laminar. If it is greater than 10 raised to power, flow is turbulent. Now formula use. The formula number 6, 7, 8 can be used for the vertical plate. Okay, if the flow is laminar, that is the value of Rayleigh number is less than 10 raised to power 9, then Nusselt number's formula will be 0.59 and GRPR raised to power 0.25. And telling again, this formula is given in HMT data book. There is no need to cram it. Similarly, for turbulent flow, Nusselt number is this, and for calculating heat transfer, we'll be using the formula HATW minus T infinity. Likewise, formula has been given for horizontal plates. Formula number 9, 10, 11, 12, and values have been given for the different range of Rayleigh number for a horizontal cylinder. It is given in the table. Similarly, for horizontal cylinder, heat transfer Q is equal to HA and A is equal to pi TL. Similarly, formula can be used for the sphere. And for getting the boundary layer thickness, the formula is this. And for maximum velocity, the formula has been given. All the formula has been given in the data book. There is no need to cram.